Hi everyone, welcome to my YouTube channel. In this video, I will show you how to do some important pump calculations. In this part, I am covering differential head calculation for pump. I will also show you how to estimate NPSH available. In part 2, I will cover how to estimate pump power and how to calculate some benefit calculations. But for now, let's focus on this current part 1 video. To demonstrate the framework about how to estimate this differential pressure, I have taken example from the book Process Engineering and Plant Design by Siddharth Mukherjee. I will also introduce my own Excel add-in that will be an excellent companion in your learning path of hydraulics calculations. So without wasting much time, let's start with the pump example. In this example, we want to install a pump for this system. Here we want to transport a liquid from feed surge drum to the top of this water wash column. So we need to estimate the differential head that pump needs to generate to effectively operate within a given system. So before we get into the rigorous Excel calculation for differential pressure, just want to talk about framework or outline of this calculation. So for the differential pressure calculation around this pump, first we need to do calculation on the suction side and then on discharge side. So on suction side, we need to take care of these 5 different calculation components. Like first is about suction side vessel pressure. So here we will talk in terms of head. So we will talk in terms of meter. So how much pressure is there in this suction side vessel? We also need to know how much suction side static head. So this is the liquid level in this surge drum with respect to the pump center line. We also need to deduct that suction side head loss that is happening because of frictional head loss through the pipe. We also need to deduct like suction side head loss through fittings and valves. So whichever fittings and valves are there on the suction side, we need to account for the frictional head loss because of those things. Suction side head loss that is happening because of equipment on suction side. So if we have any equipment on suction side, we need to deduct that component as well. On discharge side also, we have similar 5 components. Like on first one is the discharge side vessel pressure in meters. The discharge side static head, so that is the inlet nozzle elevation with respect to the pump center line. Then discharge side head loss through the pipe. So whatever frictional head loss that is happening because of the flow of liquid through this pipe, that also needs to be added. Then discharge side head loss that is happening because of fittings and valves, those are present on discharge side, and very similarly the head loss because of the equipment that is present on the discharge line. So now we will get into Microsoft Excel to do this calculation in very systematic way. Now coming to the solution, I have already solved this example on Excel. I will take you through this solution step by step for proper understanding. You can always download my Excel file from the link mentioned in the video description. So starting with this example with what type of information is already provided to us. So here the fluid properties are given. So maybe let me bring this schematic. So fluid that we want to transport here is the water, and this water is available at 30 degrees centigrade. The temperature is important because of the fact that we want to know vapor pressure as well. So vapor pressure is a function of temperature. So for that purpose, temperature is given. The flow rate for which we want to do this calculation is also given. It's a normal flow rate. So most of the time pump would be transporting our liquid with this particular flow rate, 36 meter cube per hour. Density is known to us. Viscosity 0.7 centipoise given to us. The vapor pressure is also given to us 0.042 kg per cm square absolute at 30 degrees centigrade. Now we have both kind of information, like from suction side conditions are also highlighted in that particular example. Discharge side conditions are also given to us. So one by one, let me take you through those things. So starting with the suction side. So in suction side, the static height is given of 2 meters. So static height here is like the elevation of this feed surge drum from the datum, and the liquid level in the feed surge drum is around 1 meter. So this is the liquid height inside this feed surge drum. Then pressure on the suction drum, that is given 0 kg per cm square gauge. So it is nothing but 1 atmosphere. It is just that atmospheric pressure. The suction side pipe size is given in terms of meter 0.15. So this pipe size is 0.15 meter. Okay. Straight length of suction piping is 3 meters. So this length from here to here, inlet nozzle of the pump, that is around 3 meters. The density, it is just repeated here. Okay, the density of the liquid is this much. Now coming to the viscosity. So viscosity in Pascal second is this much, 0.0007. The information that is given to us, viscosity is 0.7 centipoise, but we would be more comfortable in calculation Pascal second unit. So we can convert it. In case if you don't remember this unit conversion factors, you can always take help of this TPG-XL add-in. So in this TPG-XL add-in, there is unit conversion group is there. There's also some hydraulics group. I will talk about this hydraulics in a moment. But before that, in unit conversion, you can select the viscosity in. So we have viscosity here, and so centipoise to Pascal second. So we can quickly get to know, okay, 1 centipoise is 0.001. So we can easily calculate Pascal second. Then there is a pipe roughness that also needs to be given. So here this value, so for this pipe roughness is used in the calculation of friction factor. So for that purpose, we need to give this. We typically don't remember this. We take this value from Perry. So for commercial steel pipe, you can consider this pipe material here, and you can just click this commercial steel or wrought iron, and you can get to know like, okay, this is the roughness in meter, 0.0000457 meter. You can quickly use this information here. Or otherwise, you have to open your Perry's handbook and you have to check like, okay, for my steel, commercial steel, what is the typical roughness value. Then velocity is something that we can easily calculate because all this information is available to us. What is the flow rate, then what is the pipe size. So we can calculate this velocity in meter per second. Reynolds number is something that also you can easily calculate because it's just du rho divided by viscosity. So you can do this calculation. I have also developed my own built-in function that can help you to calculate this Reynolds number. So for that purpose, you need to do just like click equal to sign TPG underscore. So I have developed two inbuilt functions, that is a friction factor and NRE. So here we would be using NRE, and just click Control Shift A just to get to know like, okay, what input parameters it requires. So here you need to just insert this diameter in meters. So okay, this is diameter in meter. Then velocity in meter per second. Okay, we have velocity in meter per second. Then we also need to give information about density in kg per meter cube. So it is here. And we also need to give viscosity in Pascal second. So that is here. So if you click this, you get the very similar answer. You can also use this built-in function, or you can just use your formula-based calculation. Once Reynolds number is known to you, you can calculate friction factor. Here, we would be using famous Darcy-Weisbach equation to calculate frictional head loss. One important parameter here is the Darcy friction factor. Typically, it needs to be calculated using Colebrook-White equation. This equation is implicit in F and demands iterative procedure to estimate the friction factor. Fortunately, there are few approximate methods are available which bypass the need of iteration. Here, I have used Hallen's approximation. My user-defined function is also coded with Hallen's equation to help us calculate Darcy friction factor. So here, the Darcy friction factor is calculated using the Hallen's approximation. In case if you don't remember this equation, you can also use the built-in, the user-defined function that comes with our TPG-XL add-in. So you need to just click equal to sign with TPG, and you can see the friction factor function is there. Now what inputs are required? You can put the inputs in two different ways. One way is just by clicking the fx function, and you can figure out like what inputs are required. But I would suggest you can do another way, that is TPG underscore friction factor tab Control Shift A. This will just let you know, this will guide you like, okay, what is the first argument needed, that is NRE. So Reynolds number, then diameter in meter. So here the diameter is this much, and epsilon, that is the roughness in meter. So roughness is here in meter, and closes. So it's the same function, the same formula is there in this function. Just deleting this for now. So now coming to the fittings and valves. So pressure drop or frictional head loss that is offered by fittings and valves. So we need to tabulate all the fittings and valves. Those are present on suction side. And for each fitting and valve, we need to provide a K value as well as a quantity. So as per the problem, we have two bands, one gate valve. And here we have been using single K value method. There is also 2K method is available, but for simplicity purpose, I'm using single K value method. And you'll be able to find these K values for different fittings and valves from the Perry's handbook or from Gavin Towler's book. I have also summarized some important fittings K values in this particular Excel add-in. So you will be also able to see like for different bands, for different elbows, for different gate valves, what kind of K value that you can use. So for preliminary calculation, you can definitely use it. So here we have bands to quantity, and the K value is 0.75. So you can also find out from here, like we have a 90-degree band, so 90-degree elbow with R by D ratio 1. So that is coming 0.75. So we can use this value here. In case if you don't have number, you can, for preliminary purpose, you can find out from this Excel add-in. For gate valve, let's assume that this gate valve is a half open. So gate valve half open, it is 4.5. So you can put the K value here, 4.5, and you need to figure out what is the total K by this way, 2 times 0.75, 1 time 4.5, summation of this total K value. So total velocity head is actually, so K times velocity head becomes your frictional head loss, or the head loss that is happening because of fittings and valves. You also need to summarize what equipment are present on your suction side. So here we have a strainer, and pressure drop, we can take some typical value in the early stage, like here as per the textbook it is 0.05 kg per cm square pressure drop. In case if you don't have some guideline numbers, you can use the same Excel add-in where I have provided few equipments with typical pressure drops, like for coalescer, for heat exchanger, for pump suction strainer. So it is showing 0.07 kg per cm square. So here, since this number is already given, I'm not changing, so it's 0.05. Now very similar way, you need to do calculation, or you need to summarize this information on discharge side, like what is the static height, what is the pressure on the column top, discharge pipe size, straight length of discharge piping, density, viscosity, pipe roughness, velocity, and Reynolds number, friction factor. Everything needs to be calculated. Very similarly, we need to summarize what fittings and valves are present on discharge side. Here, as per the problem, it is given, it's a bands, gate valves, check valve, swing type, and you can always, visit this TPG add-in and figure out how much K value is there we can take for different fittings and valves. What equipment are present, like for control valve pressure drop, you can preliminary you can take it like 1 kg per cm square. Heat exchanger, it's like a liquid heat exchanger, right? So in that case, you can select. So I have also provided here like heat exchanger liquid. So typically 0.3 to 1 kg per cm square pressure drop is expected. So here we have taken 0.5 kg per cm square as a expected pressure drop. Flow orifice is 0.2. We have also flow orifice here. It's like 0.14, but I have taken this value from the book. So this is more conservative. So let's stay with this 0.2 kg per cm square. Once you are ready with this two things, now the calculations are much easy. Now first we will do calculation on the suction side. So on suction side, different calculation components are there as we discussed earlier, and for each calculation component, we have a dedicated box where we have done the calculation. For example, on suction side, vessel pressure is 0 kg per cm square gauge. We need everything in meters, in head. So we need to first convert this gauge into absolute. So converting this gauge to absolute is not that difficult. You can, if you don't remember the conversion factor, you can just visit this Excel add-in and you can go to the pressure, and we need to know 1 atmosphere. You need to know 1 atmosphere is how much kg per cm square. and maybe let's use 5 decimals. So maybe we can just use this number 1.03323 that needs to be added to make it absolute, and 1 kg per cm square is how much Pascal. So kg per cm square to, sorry, not psi, but Pascal. So you just need to copy this number 98,066.5 Pascal, and you can just convert in Pascal. Once things are in Pascal, it's very easy to convert into meters by P divided by rho g. So you will get this 10.41 meters. That much head is provided by the suction side vessel. Then suction side static head, it is a very simple suction side static head is like 2 plus 1. So I have just referenced this cell, static height plus liquid level, 3 meters. Then suction side head loss through the pipe. Here we are using this Darcy Weisbach equation, F times L by D times velocity head. So we have already calculated everything here. So friction factor is there, velocity is there, then this is the length L by D. So L length is there, pipe size in meter, that is there. So you can easily calculate this, how much head losses happen. It has a negative impact, so it will be deducted. And suction side head loss through fittings and valves, so that is K times velocity head. So total K, this multiplied by velocity head, V square by 2G. So like that it is calculated. Suction side head loss because of equipment. So we have only one equipment, that is strainer 0.05. That is 0.05. So that has to be converted into meters. So the P divided by rho g is converted. So it is in meter. 0.05 is equivalent to 0.5 meter of head. So suction side head. So at the pump nozzle, what is the suction side head that we are getting is just this formula, 1 plus 2 minus 3 minus 4 minus 5. So we are getting around 12.8 meters. Similar way on discharge side also, we have discharge side vessel pressure is 1 kg per cm square gauge. So we can convert absolute, Pascal and meter. So this much meter head we need to generate, that is required at the inlet nozzle of our water wash column. Discharge side static head is just a 30 meter, that we know is 30 meter from the pump center line. Then discharge side head loss through the pipe. So it's just the head loss because of friction. So that is again Darcy Weisbach equation. Then K times velocity head. Then different equipment we have. So all these 3 equipment like control valve, heat exchanger, flow orifice, and we need to convert everything into head. So discharge side head is like 69.33. This is coming. So now it's very simple to calculate how much differential head that our pump need to generate. So that is nothing but the difference between this value and this value. So that is coming around 56.53. So once you know the differential head and the normal flow rate, you can select the appropriate pump model for your service. Now we will focus on how to calculate NPSH available. So for that you would require the vapor pressure. So vapor pressure information is something that is already given to us. It is 0.042 kg per cm square absolute. We need to convert this pressure into a head. So it is converted into the meter, so 0.423 meter. And NPSH available is nothing but your suction side head minus your vapor pressure head. So this is like 12.38 meter head is available to us. Now for a given model, there would be different NPSH required. Let's say the pump that we have selected, it has a requirement of 2 meter. So the margin between NPSH required and NPSH available is 10.38, which is pretty large. So normal rule of thumb to avoid cavitation is like the margin should be more than 1 meter. Here it is very high, so we are in good side. But this becomes very critical, especially when we are dealing with pumping the liquid, which is at its boiling point, where its vapor pressure is very high. In that case, maintaining margin is very crucial. So we have now reached to the end of this video. I hope you have found this video helpful. You can download my Excel file with Excel add-in from the link mentioned in the video description. Thanks for watching.